Good afternoon to you viewers and subscribers, and welcome back to another video. I am Belly One Engineering, where I present to you construction and engineering topics as it relates to building construction in Jamaica. Now, in my last video presentation on specific gravity as it relates to coarse aggregate for design concrete mix, there was a small error in one of my calculations. I think it was when I was calculating the bulk specific gravity. So I'm going to use this video presentation to correct that mistake. But my topic for this week is going to be finest modulus for coarse aggregates. So stay tuned for that presentation. Thanks. Now, as I've stated to you in my intro for this video, that in this week's video, I'm going to be presenting to you the lab procedure for calculating the finest modulus for the coarse aggregates. Now, conversely, I must point out to you that you can repeat this same procedure, a similar procedure, to calculate the finest modulus for your fine aggregates as well, because that is also going to be needed to determine if your material for your design concrete mix as it relates to fine aggregates is suitable. Therefore, the first question in this presentation is that you want to know what is finest modulus as it relates to coarse aggregates. Now, the finest modulus of coarse aggregates represents the average size of the particles in the coarse aggregate by an index number. The finest modulus is determined by performing the sieve analysis with standard sieve sizes. The higher the aggregate size, the higher the finest modulus, and hence the lower the aggregate size, the lower the finest modulus. Therefore, the finest modulus of coarse aggregate is higher than the finest modulus for the fine aggregates. And what this simply is saying is that when you carry out your lab procedure and calculate the finest modulus for the coarse aggregate, whatever value you have gotten, it is going to be higher than the value of the finest modulus as it relates to the fine aggregates. Now, how to find the finest modulus of coarse aggregates? Now, to find the finest modulus of coarse aggregates, we need the following sieve sizes. We need the 80mm sieve, the 40mm sieve, the 20mm sieve, the 10mm sieve, the 4.75mm sieve, the 2.36mm sieve, the 1.18mm sieve, the 0.6mm sieve, the 0.3mm sieve, and the 0.15mm sieve. So you're gonna need all these sieve sizes to do the sieve analysis for the coarse aggregate in order to calculate the finest modulus. Now, the second aspect of this procedure is that you have to arrange the sieve sizes in descending order and put the arrangement on the mechanical shaker. So you're going to put the bigger sieves at the top and the smaller sieves at the bottom, and you're going to place that arrangement on a mechanical shaker. Then take an oven dry sample of about 5,000 or 5,000 kilograms. Now I just use this figure as a reference point, but you can take whatever sample weight you want to carry out the procedure to calculate the finest modulus. And you're going to place that sample weight in the top sieve of 80mm. Then you're going to place a lid and a pan at the top and bottom of the sieve set respectively, and you're going to shake it on the mechanical shaker for about 15 to 20 minutes approximately. Now, after proper sieving is done, you are going to record the sample weights retained on each sieve and find out the cumulative weights of retained particles as well as the cumulative percentage retained on each sieve. So you're going to record the weights of each retained aggregates in the respective sieve, and you're going to write down, you're going to record those weights on a separate table. I'm going to show you a practical demonstration of this calculation in this video to come. So when you have done that, you're going to finally add all the cumulative percentage values and divide that result by 100, and that is going to be the finest modulus for your coarse aggregate. And I want to point out to you that the range of your finest aggregate is between 6 to 8. So when you calculate the finest modulus for the coarse aggregate, you must get a value between 6 and 8. Anything outside of that, then that aggregate is not suitable for your concrete mix design. So what I'm going to show you now is the arrangements of the sieve sizes that is placed on the mechanical shaker. So this is a visual depiction of what the procedure looks like in a materials laboratory.
So as I pointed out to you in my intro, there was a error in my calculation last week for the bulk specific gravity, which works out to be 114. If you look back at that video, you will see that the bulk specific gravity was 114, and sorry to say that is not correct. So I'm going to do that correction right as I'm speaking to you. So if you look at the formula for bulk specific gravity, it was weight of oven dry, which is 29.72, over the weight of saturated surface dry, which is 29.98, minus the weight of weight of aggregate submerged, which is 18.51. And if you notice here, I have 29.72, which is not correct, and that results in the error of 114. So I'm going to correct that. So this 29.72 should be 18.51. Should be 18.51. Right? So this works out to be 29.72 over 29.98, subtract 18.51 from that, and that works out to be 11.47, and it's going to be 29.72 divided by 11.47, which works out to be 2.59. So therefore we have it, the bulk specific gravity works out to be 2.59 instead of that 114. So it is the bulk specific gravity 2.59, the bulk specific gravity at SSD, at saturated surface dry, which works out to be 2.61, and the apparent specific gravity works out to be 2.65. So my mistake, and I apologize for that miscalculation. So you can go now and see the correct calculation for the bulk specific gravity, which is 2.59. So welcome to the presentation or the tutorial of the lab procedure in terms of calculating your finest modulus using the self-analysis. Now, as you can see in the first column is our sieve size, and our sieve size ranges from 80 millimeter to 40 millimeter to 20 millimeter to 10 millimeter, 4.75 millimeter, 2.36 millimeter, 1.18 millimeter, 0.6 millimeter, 0.3 millimeter, and 0.15 millimeter. Now in our second column is the weight retained in grams. So I must point out to you that the sample size for this procedure is 2,500 grams of coarse aggregate, and we put that 2,500 grams of coarse aggregate in our top sieve of 80 millimeter. Place it on that mechanical shaker, shake it for approximately 15 to 20 minutes, and after that is concluded, then this is the weight of the aggregate that is retained in each respective sieve. Now, if you look at the 80 millimeter sieve, you will see that 0 aggregate retained. If you look at the 40 millimeter sieve, you will see that 125 grams of material retained. The 20 millimeter sieve, 875 grams of material was retained, and the 10 millimeter sieve, there was 800 grams of material retained, and the 4.75 millimeter sieve, 700 grams of retained material. And from 2.36 millimeter down to 0.15 millimeter, you can see that 0 aggregates was retained. So what that means is that the sieve size of 2.36 millimeter down through to 0.15 millimeter, the sieve size is so small that the coarse aggregate was not able to fell through when it was shaken. So one observation that I want to point out to you, that if you notice that the sieve, which is 4.75, it was 700 grams of material retained, and from that downward you can see that 0 material was retained. So if you should total from your 80 millimeter sieve to your 4.75 millimeter sieve, this total supposed to come back to this 2,500 grams of material. So how we can prove that that is the case? We have to do the cumulative weight of retained material in grams. So the first weight of material retained, it was 0. So we bring back our 0 across, right? And then to get the cumulative weight, we had to add this 125 to 0, which comes up to be 125, right? Then this 875, we had to add it to this 125. So it is going to be 875 plus 125. That is going to be 1,000, right? And this 800 grams, we're going to have to add it to this 1,000 grams, which works out to be 1,800, right? And this 700 grams, we have to total it back to this 1,800 grams, which works out to be 2,500 grams of retained material. So from there on, you can see that is 0 weight of material that was retained, right? And that we can carry across this. So it's going to be 0 plus 2,500, which is going to work out to be 2,500. So you can see at the 4.75 millimeter sieve that it is 2,500 grams of material in total. If you should total the weight cumulatively, it comes back to our 2,500, which come back to our sample size of 2,500 grams. So we can continue with this process. So this is 0. So we're going to carry back our 2,500. 0 again, our 2,500. 0, 2,500. And then 0, which is 2,500. So as you can see now, this column represents the cumulative weight of retained materials after it has shaken in the respective sieve. So The next step is we want to calculate our cumulative percentage retained, and the cumulative percentage retained is the cumulative weight retained, right? Which is, in this case, is going to be 0 over the sample size of 2,500 times 100, right? And this is going to work out. This is going to work out to be 0. So you have to count that 0 here. So that works out to be 0, right? Because anything divided and multiplied by 0 is 0, right? So we're going to work out now our 125. So it's going to be 125 over 2,500, which is our sample weight. So it's 125 over 2,500 times 100, right? And that works out to be 5, right? So we carry a 5 here. We do the same thing for this. So this is going to be 1,000 over 2,500, 1,000 over 2,500 times 100, right? So 1,000 divided by 2,500 times 100. This is going to work out to be 40, right? Carry over 40 right here. We do the same thing for this 1,800. So it's going to be 1,800 over 2,500 times 100, right? So 1800 divided by 2,500 times 100. That works out to be 72, right? So we carry our 72 right here, right? Right? And this is going to work out to be 2,500 over 2,500 times 100. So we're going to get back 100 right here, right? Same thing for this 2,500. It's going to work out to be 2,500 over 2,500 times 100, and that's going to work out to be 100. So we have 100 here, right? It's going to be another 100, 100, 100, 100, right? So to calculate our finest modulus, is a summation of cumulative percentage retained over 100. So if we should total this column, the cumulative percentage retained, so we're going to total all these figures. So we have 5 plus 40 plus 72 plus 1, 2, 3, 4, 5, 6, so that's 600. And that works out to be 717. Right? So therefore, our fineness modulus works out to be 717 over 100, which equal to 7.17. Right? So there we have it. Our fineness modulus works out to be 7.17. Our fineness modulus works out to be 7.17. And one thing I want to point out to you, how you can verify if your fineness modulus for your coarse aggregate is suitable for your concrete mix, if this coarse aggregate is suitable for your concrete mix based on the fineness modulus. The range of the fineness modulus for your coarse aggregate should range between 6 and 8. So this is 7.17, so that proves that this calculation for the fineness modulus is within range, and therefore your coarse aggregates is suitable for your concrete mix. So should you calculate your finest modulus and you're getting anything outside of this, if you're getting below 6 or you're getting below above 8, that means your coarse aggregates is not suitable for your concrete mix design. So that is it for this video. If you like the video, please remember to share the video, leave a comment should in case you have any questions, and as usual, I'll be very happy to answer your question. Don't forget, if you're watching this video for the first time, to subscribe to my channel, and I will see you in another video upload. Thank you.